In this presentation, I'm going to introduce two Persian preprocessing utilities, E4MT and LMBNC. In order for model to produce quality outputs, we should provide it with quality inputs. So we process raw data prior to feeding it up to the model. Some of most common preprocessing operations applied to text corpora are normalization, tokenization, spelling correction, and etc. When we have access to large amounts of data, the model may learn to compensate for the shortcomings of inputs, but facing low resource situations, the importance of preprocessing becomes prominent. One sample shortcoming, and maybe the most important one, in text corpora is existence of several different representations for the same word, which reduces the chances of the model for encountering similar patterns during training. Persian, which is an agglutinative language, has several written forms for many of its words. This basically comes from two facts. First, there are several characters that represent the same letter, and second, different writers use different methods of writing for compound words. We have developed one such text preprocessor named E4MT, which stands for Essential Tools for Machine Translation. In fact, this preprocessor can be used for NLP use cases, but our primary focus has been machine translation. It is developed using C++ to fulfill our production environment requirements. We have to do preprocessing as fast as possible. It contains all essential required modules like normalizer, spelling corrector, tokenizer, detokenizer, and entity tagger. It is open source and GPL licensed. And as Python has become the most popular development tool among NLP researchers, we have developed a Python wrapper for E4MT as well. We use it extensively in our services and products like Terjumyar and Tergoman, and although we tuned it for the Persian language, but it can be used for other languages as well. The normalizer module in E4MT is the most important module of all. It converts characters to their canonical form and covers the whole range of 2-byte UTF-8 code points. This is important because letters have various representations in Unicode, especially for Arabic script languages. For example, letter K has 32 different code points based on our script of choice. It also handles multi-letter symbol code points and decomposes them to their letters. For Arabic script language, there is yet another issue. When we extract text from PDFs or use OCR tools, we get glyph codes instead of the actual letter. This means we have different codes for same letter considering its position in the word. E4MT handles this inconsistency as well. Overall, normalization reduces the vocabulary size, which means the number of representations of each word is reduced. The spell corrector module tries to unify representations of words even more. It corrects common misspellings present in digital Persian corpora. It also handles superfluous and missing ZWNJs, zero-width non-joiners. For example, multiple consecutive ZWNJs serve no purpose, or ZWNJs followed or preceded by a space are superfluous. It also tries to identify parts of compound words and concatenates these parts using ZWNJs when necessary, unifying representation of those compound words. Breaking text into words or subwords is called tokenization in NLP. A naive way of doing this is by breaking text whenever a space or punctuation is present. But there are several instances where punctuation quote points are used for other purposes. For example, a period between two digits does not stand for full stop. Comma is sometimes used to separate thousands in numbers. Another example is numbered list, where the period does not correspond to end of sentence. Considering these cases, the tokenization module of E4MT first identifies numbers, email addresses, abbreviations, dates, lists, and URLs. Remainder of punctuation marks in the text then can be considered actual punctuations. This module also uses spell correction to prevent spaces mistakenly inserted in text from breaking words into parts. This table shows most frequent representations of the compound word natijegiri, which has been seen approximately 30,000 times in our corpora and in 22 different written forms, which are a mixture of spaces, ZWNJ, and control characters. The most frequent among them has a space between the two parts of this word, which is not desirable. Using different modules of E4MT, all these 22 different forms are converted to a single proper representation, which is natije, ZWNJ, and giri. In low-resource languages like Persian, the errors in training corpora can affect the quality of service and user experience. We have encountered a few cases of dissatisfaction of this nature where translation quality was heavily shadowed by obvious misspellings. Inspecting the problem, we noticed there are incorrect engrams in our training corpora. We encountered two kinds of problems of this nature. There were some unigrams mistakenly concatenated to each other, like in mutalae, and some unigrams broken into two parts, like kamelan. In some cases, corrections can be made using simple rules, like in afrod, which is a meaningless word in Persian language, and we know for sure that it has to be changed. But some need considering the context. For example, serve is a proper word for itself, but it can be concatenation of sar and va. To address this problem, we first generate viable alternatives for each of the sentences, then use a language model to score each of these alternatives, and finally select the one with highest score. This way, we incorporate the context of the sentence in identifying and correcting the mistakes. The aforementioned language model plays a crucial role in the process. We first trained a general domain language model. A combination of several corpora was used to train the language model using more data. Using this language model, we tried to correct the mistakes of our domain-specific corpus. Although many context-dependent misspellings were identified, the side effect, which is number of mistakenly changed words, was not negligible. To mitigate the problem, we trained the language model on the same corpus that we wanted to improve. The results were desirable, where both many incorrect engrams had been corrected and the number of incorrectly changed words was negligible. To generate alternatives for the sentence, we split its unigrams and concatenate its bigrams. and check if the resulting bigram or unigram has been seen more frequently in the corpora. This is done in a recursive manner. These heuristics are put in place to prevent applying unwanted changes to the corpora. In this slide, we can see examples where LMBNC has successfully incorporated context in deciding whether to concatenate two unigrams. We choose machine translation as a downstream NLP task to evaluate E4MT and compare it to two other publicly available Persian preprocessing toolkits, HASM and Parsivar. To investigate the effect of these tools on machine translation task, an English to Persian transformer model was trained using Marian toolkit. For all of the empty systems, we process the training, development, and test datasets by one of these tools and evaluate the systems using automatic measure BLUE. The experiment has been done on two English-Persian parallel corpora, a publicly available corpora, an in-house corpora which is 5 times greater. We can see their statistics in this table. And as we can see in this table, applying E4MT improves the BLUE measure over both HASM and Parsivar. Our experiments also show that approximately 4.5 million Persian tokens of our corpora have been corrected by E4MT, which is about 50% of the corpora running words. To inspect the precision of these corrected words, we select 100 sentences randomly, and 97.9% precision was observed. E4MT also reduced the vocabulary size by approximately 54% on total running words, 64% on singletons, and 35% on non-singletons. In this slide, the effect of LMBNC on machine translation is shown. As we can see, an improvement of 0.6 BLUE is achieved. Also, the accuracy of the correction process was evaluated manually. Manually inspecting 300 randomly selected sentences, we observed 98.1% precision. Thanks for your attention.